using the Lorentz-Gauss transformation. Now, let us, using that knowledge, let us come to something called a retarded potential. So, retarded vector potential and retarded scalar potential, or retarded potential in general, will call the find out the retarded potential. Now, these are the two equations for the vector scalar potential and the vector potential, the two wave equations. If you look on the left hand side, we have the potential terms or potential for field. On the right hand side, we have the source. So potential or field are on the left hand side of this wave equations, right hand side is source. Now assume that in free space there is an infinitesimally small volume V which contains the source. The source can be the current source or the charge or both of them. So there is an infinitesimally small volume which contains the source. The position vector of this volume, or the center of this volume, is R dash. So remember this, throughout this course, when we will define a source, whatever may be its nature, the position vector of the source is always dashed. So we will use a dash to describe the position vector of the source. So in this case, the position vector is R dash. From the origin, you connect to the center of the source. S is the source point. So from origin to S, that vector is R dash. We have a volume there. The source is U. U can be J or rho. So if J is the volume density or rho is the volume density, then U is equal to volume density into dq bar, or the volume of the infinitesimally small area is the dq bar. So dx dy dz or dr d theta d phi into sine square theta, so that in that form it will be there. So U R dash, now look at this, the position vector is R dash, time let us say is T dash. So since position vector is R dash, time we will say T dash. Then we are considering a field point which is far away from the source, where we are observing the effect of the source. So that field point is at point P. So OP vector is equal to R, its position vector is R. So at OP we have Ft is equal to either A or Phi. So at P the effect is it creates a scalar potential or a vector potential. Either of these two can be represented by Ft. So now if you use this concept in the wave equation we can write as del square U minus 1 by c square del dou t square dou square t U is equal to Ft. So that is how we can write it on the wave equations using this concept. Now on the position vector of P is R, position vector of S is R dash. Then from S to P, the vector between S to P, the vector which joins point S to point P, that will be capital R, and that will be the difference of R and R dash. So therefore capital R magnitude or absolute of capital R is equal to absolute difference between R minus R dash. So with this picture let us move forward, and we define something called retarded time here. T dash is with U. So this T dash we define as T minus R by C as the retarded time. Why? We define it as the retarded time. Retarded means negative time. So a movement in time in negative direction. Now we have a source S, we have a field point P. Now if we are observing something at P that has started at, or that has been initiated or generated at S, that has moved to the point P, for moving to the point P, it takes a time. What will the time? Time will be the the distance covered by the velocity. That much time it requires to travel from the source point to the field point. So the distance is r, velocity or speed with which it is traveling is c. So the time required to travel from S to P is r upon c. If we are observing the field at a time t, at the field point P we are observing the field or observing the potential at a time t, then that was generated at the source at a previous time, which is t minus r upon c being the time required for it to travel from S to P. So t minus r upon c is the time when it was generated. So t minus r upon c, we call it t dash as the retarded time, because the present time is t. A negative travel in the t gives us t dash is equal to t minus r upon c. This is called retarded time, and the potential corresponding to retarded time is called the retarded potential. Now from this we can know that the system is causal in nature. Causal means it has a cause-effect system. There has to be a cause to have an effect. At P we are observing the potential. For the potential to exist at P, there has to be a cause, which is the source. So there is a cause, which is time-dependent source at the point R dash. Similarly, there is a response, which is the field or potential at the point R. So therefore, we can write now the wave equation as del square U minus 1 by C square dou square Tu is equal to Ft. U is either rho or A, and Ft is either 1 upon epsilon rho minus 1 upon epsilon rho or minus mu J. That is what is F, and U is equal to phi or A. So that is what is the wave equation. Now suppose the wave is the origin, we shift the origin to the source point. If we shift the origin to the source point, then r dash is equal to 0. If r dash is equal to 0, in that condition, capital R is equal to small r. Now we look at the solution for retarded potentials. The solution for the retarded potential is the Green's function. If you look at the wave equation, the solution for the wave equation is given by Green's function that we already have seen earlier. How to find out the Green's function for when we discussed about potentials earlier. We have seen the solution for Green's function. So gxt, which is the Green's function, is equal to 1 by 4 pi r delta. This delta is the Dirac delta function. Delta t minus r by c. Small r, why small r? It should be delta t dash. T dash is equal to t minus capital R by c. Capital R is equal to small r when r dash is equal to 0, or the origin is located on the source. So this is what it is. Gxt is equal to 1 by 4 pi r delta t minus r by c. The solution to uxt using this Green's function, gxt, will be of the form uxt is equal to, you know what is it, we take the convolution of the Green's function with ft. So here the convolution, if you take the convolution, it will be gx minus x dash t minus theta tau. Then f is on the right hand side. So therefore the source term is f x dash tau, then k square d tau d cube x dash. That gives you 1 by 4 pi. For g you will put delta t minus tau minus r by c divided by capital R, f x dash tau d cube x dash. Now when you take this this integration 0 to t delta t minus tau minus r by c r and d tau, operating on f x dash tau, that gives us f of x dash t minus r by c, that is from the property of delta function. As you know, integration of the delta function, so integration of delta x minus x0 fx is equal to f of x0. So use that property. Using that property, we get this. So this integration will be 1 by 4 pi integration over dx dash or integration over x dash from minus infinity to infinity, f operating on f of x dash t minus r by c divided by r. So this is what is uxt. This is the solution. Now if this is the solution, urt is equal to art, frt is equal to minus mu j, or urt, when urt is equal to phi rt, frt is equal to minus rho by epsilon, that we know. Using that, we will get art is equal to 1 by 4 pi integration mu. Now f is minus mu j, so for that we will put integration mu j r dash t minus capital R upon c whole divided by r integration over r dash. Similarly, for phi, it will be phi rt is equal to 1 by 4 pi. Then for minus rho by epsilon, we take this minus sign, multiply that with minus sign in the integration earlier. So that gives you 1 upon epsilon. Then integration rho as a function of r dash t minus r upon c, capital R upon c, divided by capital R integrated over r dash, dq r dash, or integrated over the volume space volume. Now suppose we have a time harmonic function. If we have a time harmonic function, a function wrt is called time harmonic if it has a function of a single frequency only. So it contains only one frequency, so we can represent wrt as wr exponential minus j omega t. So if we represent that way, then art is equal to 1 by 4 pi integration mu j r dash t minus r upon c divided by r integrated over the volume. Now this, if we consider to be a time harmonic function, then art time part will be of the form exponential minus j omega t. So art will be ar into exponential minus j omega t, that is equal to 1 by 4 pi remains as it is. Then integration over volume of mu j, then r dash remains as it is, mu j r dash, so that is the space part. Then the time part will be exponential minus j omega into t minus r by c, because r by c is of the a time term. So that will be in the numerator, denominator will be r. Now that we can write as a exponential minus j omega t. From the integration we take exponential minus j omega t outside. If we take exponential minus j omega t outside, then that will be outside the integration divided by 4 pi. So on the left hand side we have exponential minus j omega t, on right hand side we have exponential minus j omega t. They will cancel out, leaving the other terms. So that gives you ar is equal to 1 by 4 pi integration mu j r dash exponential j k capital R by capital R. Capital R is equal to small r in case this is at the origin, the origin is at the source, then capital R becomes small r. So that is what it is. Then integrated over r dash. This, if you look at this equation, this is similar to a Fourier transform of j. So a r j can be represented in this manner. Similarly, we can find out the phi r j. So now let us consider the Lorentz condition in time harmonic case. If we have a time harmonic case, the Lorentz condition is divergence of a plus 1 by c square dou t phi is equal to 0. Now for a we will write ar exponential minus j omega t. For phi we will write phi r exponential minus j omega t. The minus sign is missing here, you can put that. So that will be equal to 0. Then dou t, if we take dou t operating on that, that will be divergence of A plus, sorry, divergence of A minus j omega by c square phi is equal to 0, or divergence of A is equal to j omega epsilon mu phi. Or if we take exponential j omega t, then we will get this equation that we have used here. This equation will be correct. And then the Helmholtz equation will be del square A minus 1 by c square dou t square operating on A is equal to minus mu j. Then again use the same principle, using the same principle for A with the time variation e to the power plus minus j omega t. Either of the two you can take. Using that you will get del square A plus omega square by c square A is equal to mu j. Now these are all A and J, these are functions of R only. Time already we have taken care of, that is taken out. So that gives us the equation in the form del square A plus k square A is equal to minus mu j. K square is equal to omega square by c square, or k is equal to omega by c. Now on the solution to the Helmholtz equation in the time harmonic form, if you get the Helmholtz equation in time harmonic form, its solution, let us find out. The equation is del square A plus k square A is equal to minus mu j. This is a inhomogeneous wave equation because right hand side is non-zero, left hand side is a differential equation operating on A, right hand side is non-zero. The solution technique is first find the Green's function g for this equation, then convolve j with g, then let us find out the Green's function here. Replace A with G. To find out Green's function, replace A with capital G on the LHS, replace RHS with the delta function. So minus mu j, that will be the delta function. Then find the solution for the corresponding differential equation. So what will be the differential equation? That will be this del square G plus k square G. A we have replaced by G. Right hand side is equal to minus, and del QR, it is a 3D function. So this is minus del QR. This is the differential equation for the Green's function. Now this is homogeneous. The right hand side is equal to 0 everywhere except R is equal to 0. Therefore this is a homogeneous equation everywhere except R is equal to 0. So everywhere except R is equal to 0, del square G plus k square G is equal to 0. If you have got del square G plus k square G is equal to 0, its solution, the general form of the solution is GR is equal to exponential minus JKR by 4 pi R. This is equivalent to the response of the potential to an impulse excitation, because delta function is equal to an impulse. Delta and impulse are similar. So this is the response of the potential to an impulse excitation. Now once we know the Green's function, then we have to find out the solution for the potential A, that we will do by convolving J with G. So AR is equal to integration mu JR dash, then convolving it with G. So GR minus R dash integration over R dash, volume integration over R dash. That gives you the solution. Now let us come to the time harmonic field. We know divergence of A is equal to minus j omega epsilon mu phi. Phi is equal to minus divergence of A by j omega epsilon mu. This comes from this equation, simple algebraic manipulation. Then H is equal to 1 by curl of A. This we know because B is equal to H, B is equal to mu H is equal to curl A. From that you get H is equal to 1 by mu curl of A. E we know is equal to minus grad phi minus dou TA, and from that we know E is equal to gradient of divergence of A by j omega epsilon mu, because minus grad phi we know what is phi. So from use phi is equal to minus grad minus divergence of A by j omega mu, put that. So E is equal to gradient of divergence of A by j omega mu, then minus j omega A. Dou t is equal to j omega. Because time harmonic nature, dou by dou t is equal to j omega. So that gives us E. So from that we will get E is equal to 1 by j omega mu into gradient of divergence of A plus k square A. From this I give you a homework. The homework is E is equal to 1 by j omega epsilon mu into gradient curl of A. They prove this E is equal to in this form. Once you know the E is equal to in the above form, from that prove that E is equal to 1 by j omega epsilon mu curl of A. This is a simple vector identity. Prove this as a homework. With this, we come to the end of our discussion for today. What we have done is we started with some vector identities or some algebraic identities. From those identities, we saw that the Maxwell's equation, from using those identities, we saw that the Maxwell's equation can be simplified to potential, two equations in the form of potentials, electric potential and magnetic potential, or vector and scalar potentials. And then we saw how to solve those potentials, how those potentials are not unique from the basic definition. Those potentials are not unique. Then we saw how to make those potentials unique. We saw how to make those potentials unique using Gauss transformation. So once we make those potentials unique, then we considered how to solve them, finding the Green's function.